one of the cardinal rules I tell a lot of the entrepreneurs I work with, because I deal with a lot of them, is start on time and finish on time, and that'll solve 80% of your problems. So welcome everybody. I'm Jeffrey Feldman. On the Board of Governors for the YAA and co-chair of the Alumni to Alumni Committee. Once again, we've got a spectacular show tonight. It's going to be the STEM report that we're going to cover in a few minutes. And we've got a very, very interesting guest, Zlatko Minev. He also happens to be a very nice guy, so we're going to have an enjoyable hour together. As we kick in, we've just, as we said, spent a year together in this environment, which has been amazing. Masks are now coming off. People are getting back to somewhat normal, but we kind of like what we're doing. So we're having discussions now on the summer programming. I think it'll end up being sort of an every other week opportunity. So keep an eye out for it. We'd certainly like to keep all of you engaged. We've got to grow together as a community over the last year, and we'd like to continue that. We still have another couple of shows coming up. So if Kate, you want to throw up the graphic just so people can see the topics, that'd be helpful. So tonight we're doing quantum computing. You're going to hear about that from Zlatko. Next week we have our last regularly scheduled show on career pivots called "You Call This Retirement," contrasting various stages of the next stage or approaches to the next stage. We've got a couple of weeks off, and it was supposed to be the ending of the semester, and there's a reunion and other things. But we had one other STEM report that was sort of by demand that we'll be putting on for June 10th, and that'll be another biotechnology panel. So I encourage you to come to that. So thank you, Kate. We can come back off share. Great. And, it's always our mention for cross campus. If you're not on cross campus yet, join us. Kate will correct me in the chat, but I think it's cross-campus at Yale.edu. Kate, I should know it by now, but she'll put it in the chat. If you're not a member, join. It's been very exciting. So with that, I'm going to introduce Zlatko. Zlatko is he's just a really interesting, and I could say younger guy because I'm getting to be old. And he's got a Ph.D. from Yale in its physics department, really one of the preeminent groups in quantum computing in the world. I think President Salve has said it himself. We're quite excited about what they're doing, both at the research level. There's some startups coming out of there. It's some of the most cutting edge technology developments that are going on in the technology arena today. He's on the GSAA board, so he stays involved at Yale. He's been a Jefferson Award winner, so we congratulate him for that. He works in the IBM Research Center in Yorktown Heights, I believe, or it's where the T.J. Watson labs are. And I'm going to turn it over to him. He's going to tell you about himself. We're going to talk a little bit about his relationship with Yale and so forth. It's clearly his research that he'd done to get his degree, got what he does today. As much as he can't say in the IBM environment or other. So there's a lot of directions this can take, and we're really looking for, for customer input. I'll be glancing at the chat, opening up for questions and any particular direction. If you want to go more of a personal direction, that's great. A Yale direction, more quantum physics and so forth, but it should be a very engaging 55 minutes we've got. So Zlatko, why don't you take over and tell us about yourself, and this will be very interactive as we go. I give you Zlatko.
All right, thank you, Jeff. And it's really good to see everyone here. So thank you everyone for tuning in at at least 8 p.m. on Thursday, where we are. A lot of us, I guess, are based out of New York here. I'm very humbled by Jeff's introduction, and of course by the audience. It's always a pleasure to be back at Yale, and always a bit humbling because you're surrounded by amazing people like yourselves and some of the things that Jeff mentioned. So feel free to interrupt me as, in my short little 10-minute initial background presentation, and then we can take it any direction, more quantum computing based, current state of affairs, what's the latest, changing some of and dispelling some of the perceptions. Actually, open source and an open ecosystem in education is a very big thing at also IBM Quantum, so we have to talk about that. Or science outreach is a big thing, or really the latest in the quantum sphere. But to put everyone on the same page and share a little bit about myself and some of the stories we can take off, I have a couple of slides. but feel free to, interrupt and stop me. Jeff, can I just check? Are you seeing the slides?
I am, Zlatko. Everything looks great. I love the smile on your picture.
Thanks. All right, so let's just jump into it. So that's me now. That's a quantum computer behind me. Actually, as we'll find out in a minute, it's really the shell which houses the quantum computer at the bottom of it. It's the shell that allows it to cool down to negative 274.14 Celsius. That's, incredibly cold, 10 millikelvin above absolute zero. And we can talk about why you need that. But before we get there, as Jeff mentioned, for context, let me give you a little bit of an idea. So of the few things that are currently ongoing. So I lead IBM Quantum's Qiskit device design. So how do you actually design and make quantum devices? So that's a project I started and currently lead. Happy to talk about that. There's one of the first things I tried to do immediately when I had to leave Yale was, because my time was done there, was to try to get involved. And so I'm on the GSAA board, as you mentioned. I also still try to stay in touch a lot with this science outreach organization called Open Labs that I had the pleasure to start at Yale in 2012 that tries to show young kids in the New Haven and now, other areas, like we had a chapter at Harvard and Princeton and a few others, to show them what it's like to step into the shoes of a young scientist, someone like a graduate student at Yale, and to show them that it's a viable career path as well. And if you want to know a lot more about quantum computing, I host this weekly YouTube seminar with folks like Steve Gervin, who's a professor here at Yale, who you can see here in this picture. Okay, so I guess to, go into the joke of, if you want to bore people to death, is show them baby pictures of yourself. But I thought I'd start there just for cuteness. At time approximately t equal to 0, this is me reaching for books. I don't think I actually could read at that time, but apparently I enjoyed picking books up anyways. We didn't have Amazon back then, so you had to pick them up yourself. This is where I was born, in Sofia, Bulgaria, in Europe. And not long into my life there, I guess I can see that at time t0 plus epsilon, where epsilon is quite small, this is now me with an old classical computer before the quantum computers. And I can date this picture a little bit because you can see that there's an MS-DOS little Bible down here to educate that. So maybe some of you remember that. Now, I'd like to link those two pictures in my head and say that I've always liked computers. So this is the classical computer on the left in my early life. And today we'll get more to talk about quantum computers, which is where I currently spend my time, but I seem to always find myself with computers in these pictures. So what happened in between the two, and how did I go from classical to quantum? Really, the largest part of the story, and you'll see that tied throughout the whole thing, is Yale. It's Yale at Berkeley, it's Yale at IBM, and it's Yale in the middle. And those are going to be his two children. That's my kind of joke there. So Yale has a profound impact in this sphere and in this world. And if I'm not mistaken, one of them starts by Berkeley, creating Berkeley, but that's going back a lot. This is me. That's where I graduated college, moving from Bulgaria to the San Francisco Bay Area. I lived in Marin for a little bit, or Cupertino. Went to college in Berkeley, and that's where I was first exposed to quantum computing.
What was your undergraduate degree in, Zlatko?
Oh, good question. Yeah, thanks, Jeff. So I was on the divergent path between computer science and quantum computers. No, let me rephrase that. Quantum computers was not even a thing back then. I was on the divergent path between quantum physics and classical computers. And I thought, to really invent, to discover, to solve big problems, we can't really look at the same approach, as we have to get deeper new understanding to try to solve something that's impossible. So I thought physics can help me get that knowledge to discover something new and understand it, then harness it to create something. And that nudged me over to the side of physics.
Excellent.
But if I'm not mistaken, Berkeley was founded by Yale alums, so but I dropped that in there. And if there are any Berkeley College folks here from Yale, feel free to shout out in the chat. This is, I guess this is me at Yale, and then my trajectory then led me to IBM Quantum. You notice that all of these are clearly Yale related since they all share a Yale blue type of color in their logos. There's definitely some connection. So what happened in that jump? I thought in terms of diving into quantum physics, I would take a story that's quite personal and close to my heart, and I think illustrates that we're still on the cusp of discovering some profound new effects in quantum physics that allow us to extend its reach further and further. And one of those recent realizations, actually, we just celebrated 40 years of the kind of cornerstone conference that kicked off, if you want, the field of quantum computing. But that was just the seed of an idea that, you know, a number of, at the time, folks thought was an eclectic idea. It was really just a philosophical discussion. Can we use quantum physics to actually speed up computation? And these were discussions by Richard Feynman, Nobel laureate and physicist, you know, Charlie Bennett, and others. And that kernel of a seed of an idea since then has sprouted and, you know, really started to become an emerging industry. But is very close to research and applications. And we'll see that those two go hand in hand together quite a lot. And one of these interesting aspects here, I think, is to maybe share this little story of my dissertation in time at Yale called On Quantum Jumps. And I'll give you the kind of broader, bigger picture here. Oh, I see. Quantum, in a sense, is founded on two fundamental pillars that distinguish it from classical physics. These are two of the core features. And one of them is the discreetness inherent in quantum systems, that energy levels are discrete. And the other is the unpredictability that's inherent in the quantum measurement. And both of these are quite corner features of quantum physics. Now, imagine by way of analogy, a volcano. It's a bit like a quantum bit, a qubit, in the following joking sense. It has two states, a state where it's dormant and it hasn't erupted, it's just there. And in the other case, the volcano can erupt and has erupted, right? These are two, if you want, discrete states, if you entertain my analogy. Now, as we know, it's very, very hard to predict this. And in quantum physics, it's almost impossible to predict. It is in fact reputed to be impossible to predict the time at which a quantum jump will take place, when a qubit will switch from one level to the other level, for instance. And this has been kind of a long-standing tenet. Now, the work we did actually my dissertation work at Yale, something that I can tell you the story about how that came up, asked, you know, is this really the case? Or can we actually zoom into that very deep mechanism and can we look at the analogy of classical volcanoes, which, while unpredictable in the long term, you know, no one can say 2 years from now a volcano will erupt, they nonetheless possess certain telltale signs, like tremors in the ground, for instance, that if you have the right apparatus, if you have the right finesse, you can try to detect and measure. And you can use those telltale signs as an advanced warning signal to anticipate this volcano erupting or a qubit switching. So with that, to take us into the quantum world, imagine that instead of the volcano, we have a qubit or two-state quantum system, which we like to depict by two energy levels, one that's 0, the atom is not excited, or 1, the atom is excited. If you shoot it with a laser or some sort of microwave source, you can make it jump from one level to the other without it ever being, so to speak, in the middle. You would never measure its energy to be 0.5. It's always 0 or 1. And this is what we call a quantum jump for an open quantum system. And these are discrete, and also the time at which they occur is said to be fundamentally unpredictable. And the question is really, how true is this? So I happened to go to the summer school conference while I was a student at Yale that happened in Scotland, where a theorist, Howard Carmichael, quite famous, had an idea that perhaps this isn't the case. Perhaps there's actually a continuous and smooth transition, and he had a sort of theoretical description of that. But unfortunately, he concluded his talk by saying that this is way out of reach of experimental physics for the foreseeable future, even though it would be really important to understand this for quantum computers, as we'll see in a minute. Luckily, thanks to some of the awesome education at Yale and recent breakthroughs in the lab of Michel Devoret and Rob Shokov and folks, I thought maybe we could use some of these advances to actually realize this in a different world, not the world of real atoms, but the world of superconducting low temperature artificial atoms, which we engineer and have really pioneered at Yale. And we could actually look at that jump. So what this dissertation work found is that, contrary to what we've believed for a long time, if you can zoom in and look for those telltale signs, you can actually find that the quantum jump from the qubit ground state to the qubit excited state isn't instantaneous, like Bohr had predicted. It isn't totally random and discontinuous, but rather it actually possesses a continuous, coherent, and even predictable flight. Just like the same way that if a volcano is about to erupt, you can always tell before it erupted by some of those signs. Now, just like the imperfect analogy of the volcano, these quantum jumps that occur still remain unpredictable in the long term, but in the short term, they actually behave a lot like this continuous, coherent, and deterministic like evolution that is a bit less characteristic of quantum. And you can begin to use this kind of newfound knowledge to catch and reverse a quantum leap before it's even had the chance to occur. That's something that was really thought impossible until, I think, until we did this. So you can prevent, if you want, the disaster from happening, and everyone survives, if you like my analogy. So this really goes back, this particular work at Yale, my dissertation goes back to the founders of quantum, Bohr and Einstein and Schrödinger, and mixes the character of the type of quantum that Bohr had introduced in terms of the discrete energy levels that we're all quite familiar with this character of more continuous evolution, this wave nature, if you want, of quantum physics that Schrödinger had quite pioneered, and mixes in, of course, Einstein's objection to the randomness in quantum physics that he very fervently felt about. So this has been a long-standing debate about, do quantum jumps exist and are they continuous or not? And this work really begins to or rather tells us that, in fact, Bohr, Einstein, and Schrödinger were all wrong and right at the same time. They're seemingly opposing viewpoints on the discreteness and continuity of quantum jumps, predictability and lack of predictability, actually seem to coexist in nature, which is really interesting. It's just that on the long term, they're unpredictable. In the short term, they possess a degree of predictability. And it turns out that this is very important and interesting for quantum computing, because these kind of random jumps that occur due to a coupling of a qubit to the environment, we like to say, are the things that are the main limitation, the main roadblock, if you want, to the realization of large-scale quantum machines that can perform interesting computations that are otherwise considered intractable by classical computers, meaning that for certain calculations, we believe that even if you had all the computers in the world, it might take you to the edge of the universe to do a calculation using classical computers, just because of the type of restrictions that exist on the way that information is processed at a physical level. But if you had a quantum machine, you no longer are subjected to quite the same limitations. You actually live in a richer world, the world of atoms, where things can be in two places at the same time or not. And you can leverage that physics, you can leverage that newfound behavior of nature that we've never had the chance to tap into before, to perform calculations, to take shortcuts, if you want, to tunnel to the solution sometimes. And that can, in certain cases, provide, we like to say, exponential speed up over classical machines. That is, assuming that there are no random quantum jumps or quantum errors. So for me to kind of wrap up this part of the story, it was very interesting to one, understand that there's more to the story of quantum physics than we previously thought. It's not quite as discrete and random as we thought, but it also opens doors to otherwise inaccessible technology. You know, it's by harnessing these new behaviors of nature that we can create interesting and new solutions to problems that have previously seemed intractable. At the same time, as we create this new technology, that new technology opens the doors to doing experiments like the ones I just showed you, which were beyond the dreams of even the founders of quantum physics, perhaps. But because of the advances for quantum computation, for quantum computers, we can also now start to probe more on the fundamental physics and science, and those two can feed off of each other. So maybe I'll just kind of end there and pause, and I can, you know, tell you that this became Discover Magazine's, you know, top science discovery, and it's a Nature paper, and you know, MIT recognized it. It became a sort of an important, I dare say, work, or at least very widely recognized. But I think it's more fun to talk about, you know, pause there and talk about some questions about quantum and physics and really make this a little more interactive. So, Jeff?
No, Zlatko, thanks. That was clearly an eye-opening, and now that we've all got our PhDs in quantum physics, we can certainly ask you lots of questions.
And I see we have some experts in the audience because someone mentioned quantum trajectory theory. So yes, we can get into that too.
That'd be fine. I'll turn over to Charles in a moment. But I did want to ask you a question. I was thinking of it when you and I chatted last week, and again now. You know, when we were talking, I mentioned I've got PhD in material science myself. And, you know, one thing humans are conditioned to is sort of think in a framework that you know and understand. But what always fascinated me, even when I was, you know, doing studies and looking at quantum mechanics and quantum physics, was the likely association of fracture mechanics to quantum, right? Because it's also probabilistic, and it's also, you know, discrete in a way. And even when you show your volcano, you know, it's either not broken or broken, right? So I just wanted to ask quickly if there's ever been thinking or associations between fracture mechanics and some of the quantum mechanics, or the physics there.
That's a good question. I'd like to answer it like this. This is one of my other favorite quotes, and I think it was a motivator to actually this whole process. You know, when I set out to do this experiment, I had this kernel of an idea from this physicist that maybe we can do this, but I didn't have the logic. I didn't have the ability to actually prove it. So I had to go on the limb of intuition. Speaking to, you know, entrepreneurship, I think there's maybe some link there in doing this kind of science. And I think with things like fracture mechanics and so forth, you can actually draw a lot of these parallels. And a lot of even the math and algebra is I think, something that to a degree has this kind of reminiscence. So it's interesting to explore those ideas. I don't think they're heavily explored with fracture mechanics in particular, but you know, I would be interested to see where that could take.
Do you want to keep the sharing going, Zlatko, or go back to?
You know, I can stop it for now just to make it a little more interactive, and if we need to, I can pop it out again.
Thank you. And you know, for those who are in sit back mode, that's great. If we can get involved and show ourselves, that'd be great. Be active. Charles and Riley, sound like you did have some knowledge, interest, question. If you want to frame your question, have discussion with Zlatko, that'd be great.
I appreciate the offer. That was just I'd read up a little bit on Wikipedia before coming in, and QTT showed up as the as something that Zlatko had worked on. I recognized the catch and reverse quantum jump part of that when it came up in his discussion. So just a little serendipity there.
Go for it.
Yeah, thanks, Charles. Exactly. So this, you know, I mentioned that when I was at Yale as a grad student, I went to this summer school conference. In fact, and at that conference, the person who coined the term quantum trajectory theory, or QTT, gave a talk. And it was that person who had this idea, or to go back to the experiments of several Nobel laureates from the 1986, which almost 7 years after Niels Bohr proposed quantum jumps in 1913, were able to show that. Because for a long time, actually Schrodinger, Schrodinger, who's one of the chief architects of quantum physics, he wrote a paper called "Are There Quantum Jumps?" even as late as 1950s. And in this paper, which is published, and you can look it up, he wrote, and I didn't bring my Austrian accent today, so I'll do it without the accent. You can imagine. He wrote, "If all this damned quantum jumping were really here to stay, I should be sorry I ever got involved with quantum physics." So he felt, very strongly opposed to the notion that in quantum physics, which he saw as waves and a lot of wave mechanics and so forth, there should ever exist this notion of very discrete, abrupt jumps. He really abhorred that notion, and he almost polemically opposed and objected to Bohr. And of course, randomness was a whole other issue that Einstein had an argument with. And we didn't know because the technology wasn't there. It was only in the 1980s that folks were able to isolate individual quantum systems. And it was only shortly after that that people started to discuss, oh, could we use quantum systems for information processing? And again, it was at a theoretical level of like, oh, can you do it in a, in an efficient way and so forth. And so at that time, Howard Carmichael had this idea of how do we describe these new experiments which aren't explained and aren't within the jurisdiction of Schrodinger's equation. These quantum jumps are just not in there. And he started coming up with QTT, or quantum trajectory theory. And later on, he realized that if you looked at the prediction of this theory, it didn't predict abrupt jumps. Actually, if you zoomed into the time of the jumps, they were supposed to be these smooth, continuous like transitions. And in 2014 or 15, he gave the summer school talk where he talked about this, and I think he had given it a few times. And he said, this is all very interesting physics, but unfortunately, we don't know if it's true or not because we can't test it, and we won't be able to test it for X, Y, and Z reasons for the foreseeable future. And that's sort of where my link with it came in, was like, oh, but what if there is a way by going into this different domain, overcoming the challenges there? So that's that story.
That's really cool. Thanks.
Yeah.
Well, let's jump to Gaurav. I saw Gaurav had a question, then we can come to you, Shiva. Gaurav?
Yes, thank you for a very interesting talk. I was a physics major at Yale, so you brought back both good memories and bad ones. But could you explain a little bit what you mean by short-term, long-term? So I understand more long-term, meaning if you're looking, I think what you mean is if you're looking in aggregate, you sort of can't predict when one will quote unquote jump versus the other. But when you say short-term, what does that really mean?
Okay. Yeah, let me address something you said in the first part of your talk, which was, good and bad memories. So by no means, physics is, I like what I do, but there's certainly tough times and it's a hard thing, right? But we're in the business of challenging. So whenever I ran into those, because for 2 years I had no idea if this would work. And, I was in my 6th and 7th year of my PhD and stuff. And so I had to go out on a limb and had to believe in it. But this quote always kept me going. So I'm going to share this for just 1 second by Albert Einstein, and I'll let you read it. So I like to I like to remind myself of that. I suppose I've also uncovered myself. I don't actually know what I'm doing. I'm just talking here. To your second time, what I mean by long term and short term, it's really a question of time scale, and it's determined to a degree by how strongly that system is coupled to the environment. What is the environment? It means basically no real system is isolated, right? Nothing exists in isolation. Did the tree fall in the forest or not, right? And make a sound if nobody heard it. All systems are coupled to something else, and usually we call that the environment. And the strength of that coupling is part of what determines how quickly that transition happens. And the time of that transition is what we call short time. In the experiment that I did, I was able to slow that down to about a couple of microseconds. So it's quite short. In atomic experiments, that's usually picoseconds, and it's much, much quicker, much harder to resolve. But because we can work with artificial atoms, we can also artificially engineer their spectra and properties so as to slow things down on the time scale where you can have an FPGA computer intervene in real time and do feedback on it and things like that. So the long-term scale is long compared to the time of that transition, but usually that transition in typical systems happens incredibly fast to what we can resolve. unless you are able to shift things around.
Well, it comes also to the detectors, right? You've got to be able to detect the various time frames, which is always a challenge, get down to those levels.
Exactly.
I'm really fascinated. I'm wondering if I could just have a quick follow-up. I'm a data scientist now. I couldn't help notice, but your shape of your function for the transition is a sigmoid. Is that really the probability distribution of the jump, or is it that was just represented? But how does the jump actually look in terms of shape?
Yeah, that is a wonderful, wonderful question. That actually is what the jump looks like in the theory, the one I showed you. I don't know if I have my data here, but what it is, it's a hyperbolic tangent. So it's a hyperbolic tangent, and there is a very good reason for why it takes that shape. And why it's due to the randomness. There's still randomness due to the measurement. One of the fundamental things in physics and quantum, really in physics, is that information is neither created nor destroyed. It's only exchanged. And so what happens is that when your qubit or quantum system is by itself and has a weak coupling, because of that coupling, information is being exchanged. So it's giving up information. You know, somebody's learning about its state. This is how we measure it, but it must in return, by this equal rule, also get information from the environment. And that information we think of as the noise. It's the noise that drives that qubit transition. And that noise is what makes the system stochastic and if you look at what generates that curve, that hyperbolic tangent, it's precisely Bayes' rule. It's a Bayesian update, which is, particular, under particular conditions on how you update your information on knowledge, you always get the same Bayes rule. And if you iterate it, you get this hyperbolic tangent. And that's not a coincidence, actually. It turns out you can derive this type of Bayesian rule from Schrodinger's formal equations in some sense. So there's a very intricate connection there between information gain and so I don't think, Bayes, it's a quantum form of the Bayesian rule, but essentially it's Bayes' rule, but applied in a sense to quantum systems. So there's a deep connection, but maybe that's very deep physicsy. So I don't know, we don't have to go there.
Steve, I think you had a question if I
yeah. Yeah, I wanted to, Zlatko, I'd like your perspective on what are 2 or 3 problems that quantum machines have tackled that you find most exciting? Something that could never have been done otherwise. People talk about it, but I've not seen practical applications at scale yet, but I'm sure you've seen them.
Yeah, thanks, Shiva. That is a great question. And that's in a sense the $1 million, well, more than $1 million question. I think the first thing to address there is to gauge the expectations. And obviously, quantum has become one of the hottest next things after AI and so on. But you also have to, I think, put it in frame. So, 40 years ago, quantum was not even a thing. Sort of 20 years ago, people thought quantum would never work because of these quantum errors. Exactly because these quantum stochastic jumps. Then it was realized that you can actually do error correction, and you can, just the same way that in classical computers there's error correction, which it seems like you can't do in quantum at first hand, because in quantum, information is neither created nor destroyed, but it also can be copied. So you can't copy information, so you can't clone stuff. It turns out that, there are other ways to protect it. So where we are now in terms of quantum is, if I had to parallel it to, traditional computers and CMOS and so on, I would say we're in like the 1940s, 1950s of the transistor era, right? We haven't thought of the iPhone yet. iPhone is still like 60 or 50 years away or something. So while there are a lot of expectations for what's the application right now, the quantum computers we're building are advancing at a rate that keeps outpacing what I think will happen. So they're doing much, much better. But a lot of the current state of it is an emerging new technology. So, the immediate things are to look at, beyond sort of learning and education. The immediate next steps are to start to apply it to physical problems. So problems of chemistry, I'm sure you've heard of. Why? Because to simulate quantum physics, chemistry, in a sense, why not use a quantum machine, which is already quite good at describing that type of system, because it's a quantum system. So that's one of the very interesting hot areas. There's a lot of interest recently also in potentially describing non-trivial correlations in relationships, because quantum entanglement and quantum, in quantum physics, you can get some very non-classical correlations, which can be useful to describe certain patterns. So this can be useful for things like machine learning, in applications there. But, that's, again, you have to put that in perspective. I'm not saying you should go and, build your Twitter, whatever, learning bot based on that right now. These are kind of the seeds of different parts of the emerging world. And so at the current stage, a lot of this is, at the level of demonstrations and research, and we are getting closer and closer to machines that can actually do these calculations without errors, because these quantum jumps, these errors are what's going to corrupt to some degree your process, so you can't make an infinitely long calculation. But as you go from that, I think the other thing that I'm really interested in is also using the quantum computers to then also apply them to more fundamental problems, and also with some fundamental physics. I like this intersection of applied and fundamental. And
Zlatko, just to jump in, we always have the painter's dilemma. And when we get to the stage, we've got 20 minutes left. And
oh yeah, we should go ahead.
Do we go for thoroughness? We don't go for coverage. So we'll let the group decide. We've got lots of questions, so we'll just kind of handle them. We'll see what Cameron had a question, and then we've got Steve and Rob. We also had one request. If you had that Einstein quote, if you want to plop that back up for a moment. I think we would have wanted to see that. So with that, thank you. And Cameron, if you had your question, ask Zlatko.
Yeah, hey, so thanks for this presentation. I was at EECS and didn't think that much about hardware. I just assumed it was going to be this classical thing. It's going to be women, machines, and I was curious, given that when you started this work, there wasn't or you couldn't be certain that quantum jump reversal was going to work out when you started studying it. So I was curious, like, if that experiment hadn't worked out or somebody else had figured it out already, what were some of the other questions or topics that you might have ended up pursuing instead?
Well, let's go back to group mode before you kick in, Zlatko. Thanks for putting that quote back up.
Sorry?
We'll go back to group mode. Thanks for putting
Okay, yeah, great. Okay, I will do that, but first I'll show you my other fun slide that I like to have, which is believe in your ideas. So to your question, you have to commit at some point, and commit maybe for a year or two, hear the criticism. Because basically, what happened is that, I'll tell you the story real quick, because I had to consider this, right? This was actually big. In fact, I went to the summer school conference, then I came back to Yale, and I had spent like 2 weeks doing all these calculations, trying to figure this out, simulations to say that this maybe can work. I showed it to my advisor at the time, and he said, this seems interesting, but no, let's not pursue this. I think it's too hard, it may not work, and so on and so on. So that was a bit disappointing. And then I just kept working on it, talking to him. He did see that there's something very interesting there. Then at some point I presented in my group meeting with my Yale colleagues, very good top-notch people, right? In the middle of my talk on this, one of my colleagues stands up in the middle of my talk and starts shouting at me, "If this is true, then quantum physics is broken." So that's what I had to know, that's when I, well, first of all, I was taken aback because that never happened to me before. And then I had to really realize that, I'm either on something that's totally going to fail and it's going to be a total disaster, or maybe there's really something very, very interesting here. It turned out that it was very interesting, it was able to work. So the other topics that I would have considered, if I didn't make that commitment to say, let me see this through. If it doesn't end up working out, then I've learned stuff in the process, and I think that's worthwhile for me as well. I think the other thing is I was looking at before that, I was working on scaling architectures for superconducting circuits. How do you scale and how do you analyze quantum devices? Because like you said, to actually make any of this a reality, you have to have a good understanding of that, and it's quite key to actually making the thing work, the quantum computers work. There was different things on error correction and fluxonium, new qubits, things like that. So I can get more into it, but I know we are going for coverage here, so hopefully that helps.
Very good, very good. Stephen, would you like to ask your question, and then we'll get to Rob?
Oh, yeah. Thanks, Jeff and Zlatko, wonderful presentation. So I have a quick question. So, what do you think about the notion that the universe itself is a simulation through quantum computing? And the other thing is, what do you think about John Wheeler's notion of participatory universe? Like when you measure observe the jump, right? You are actually, there's a quantum zero effect. Like the more you observe, the slower things get. So you're actually participating in the jump in some sense. So like just 2 points. What do you think about the universe simulation? And what about like the participatory universe? Like what is the observer? It's very, very deep. I mean, but thank you so much. Thank you.
Yeah, thanks, Stephen. I like to take the operational approach on seeing like what is the description we can use to model things in the lab, and that happens to be the quantum trajectory theory. So that has kind of a different sense of it. It allows you to model things and describe, but it's hard to say, kind of what happens beyond that. Like where does the actual randomness really come from? Where is the measure or the observable? We have descriptions of these things, but is it a simulation? To be honest, I don't know. We can't. I'm not sure we can test that right now. You could apply kind of more Occam's razor and say, well, maybe we have these other theories. So I'm not sure I have a good answer to you on that. I'm sorry. The second part of your question was.
John Wheeler's, like when you measure jump, you're actually participating in the. Like there's something to do like with the quantum zero effect and the John Wheeler's. Right.
Yeah. So the reason I was able to do this experiment was because normally there's an environment, like I mentioned, somebody's measuring the qubit. Part of what was very difficult and was able to do was to become that everything for the environment, to become the environment for that qubit. And if I'm the environment, then I get all the information from the qubit. And that's how I can use that information to anticipate its occurrence. Now that's an incredibly difficult thing to be the sole, exchanger of information with that qubit, because there's, noise and many different things it could do. And as you mentioned, measurement necessarily and unavoidably leads to a back action force. And this is where the quantum Zeno effect occurs, because in quantum, measurement is not a passive thing. If I measure something, I gain information, hence I must put back some information. That information can also come through an effective force. So there is a sense of a quantum Zeno dynamic here as well. But I think this particular experiment, if you look at the Nature paper, sort of really goes quite beyond that. So hopefully that helps explain that a bit.
Thank you so much. Thank you.
Yeah.
Rob, you're going to take us in a little bit more philosophical direction. I wouldn't have expected anything less. So that's a good question.
Thank you, Jeffrey. Hi, Zlatko. Thank you so much for spending the time with us tonight. My question may be a bit orthogonal, and it's related to a book called The Secret by Rhonda Bynes, where she claims that through our thoughts, we can manifest things in the universe, projecting energy. And it's because of quantum physics that we're connected with something that we don't see. And I know that's not part of your dissertation, but just wondered if you might weigh in on that sort of theory.
Yeah, that's Rob from Mars. You might want to check your microphone there, Rob, a little bit.
Yeah, thanks, Rob. And I like your background, achieving leadership. That's great. So, I grew up partly in California, and my mom told me that this is very popular, and especially in California. And so there's, I guess, a large community that thinks and talks about this. I'm no expert on this, and I haven't done the studies, so I can't tell you more. I think it's also maybe a little bit easy to, take ideas and stretch them a little far, potentially. We certainly can't rule it out, but it depends what you want to do with that notion, perhaps. So I don't really have any concrete thing to add. I think I would want to see an experiment, but yeah, that's. Is it plausible? I suppose so. Yeah. Have we shown it? I don't think so. Not that I know anyway. But yeah.
Somebody else's dissertation then.
Somebody else's dissertation, yeah.
Thank you.
That's great.
Sorry, I don't have more on that.
Chuck has a question, I guess, tying in some IBM things in Cleveland and announcements. Chuck, did you want to frame that question?
Yeah, we haven't touched too much on the current state of the quantum industry. So maybe this is a good point to touch base on that a little bit. When I first started Yale, like nobody knew about quantum. Any party you went to, if you went to the Griffin's pub, just see if you're a graduate student there, you tell somebody, oh, I do quantum computing. They say, wait, what is that? Today you go somewhere and you tell something about quantum computing. People are like, oh, I read about that in Forbes last week. Are you part of this company or that company? So it's really happened very, very rapidly and quickly. I think a little bit before I joined IBM, there were almost no quantum systems in the cloud. There were not many. 2015, 16, I think IBM put the first quantum system in the cloud that people could access and control. Now there's around 30 or more. The number keeps growing, so it's hard to keep track. There are 27 qubit machines, 50 plus qubit machines. We've announced the roadmap from IBM that we're going to have 1,000 plus qubit machine in 2023, I believe. So the pace is really exponential, and it outpaces my expectations every year. The Cleveland thing is also one of the latest interesting developments that was announced. What's happened is that these quantum machines are starting to leave the research labs at places like IBM. I think one of the first ones IBM installed in Germany recently. I think there's one in Tokyo, if I'm not mistaken. That's part of this project testbed, that Qiskit Metal team that I lead. And then Cleveland Clinic and IBM recently also signed a very large sort of 10-year deal, I believe, that is going to provide an IBM quantum system and actually place it in Cleveland, and then researchers will then look at employing that. So there's this very large trend, I think, that increasingly quantum is leaping out of the lab, and a lot of large institutions are interested in learning about it, sort of getting started on it. And I think they realize that right now they can't use it for commercial value immediately, but they're onboarding and training to the expectation of what it's growing to be.
Zlatko, in that regard, just to give a quick tangent, Yale has really been setting a lot of the foundational footings for what's happening.
Absolutely.
And President Salovey speaks about it. We're all here kind of biased, but in your view, in that time frame, the next 5, 10, 15, 30 years. So while Yale had the footings for it, my question is it have the shoulders to stay in the game? Yale's a special place, but at some level, it's got its containment. So I just want to get your thoughts on that. Does it stay in the game?
That's a tough question, Jeff. I mean, tough in the sense of not that it's a tough answer, but a tricky question. I came to Yale in particular because I thought it's the foremost place in the world by far to do superconducting quantum qubits. It's also in many ways the place of origin. If you look at also most of the academic labs across the world on superconducting quantum bits, usually most of the leading labs are alumni of the Yale group. From Michel Devoret and from Rob Shokoff, Steve Gervin as well on the theory side, and more recent people as well. Shruti Puri is there now. So I think it's an absolute intellectual powerhouse, and it's continued to be that for decades now, and to lead. And I think in terms of that, as far as I can tell, it will continue to do so in the foreseeable future. And as you said, the scale is also changing at the same time to also, more commercial realizations and things like that. So there's, spin-outs and spin-offs. You mentioned, the startup earlier that came out of Yale that's, I think, still largely in stealth mode from what I can tell. So they're not talking much about what they're doing, but knowing the people that work there, I have the highest expectations and hopes. So it's a really great team, and, a lot of former colleagues. But I think I'm not just saying that because I'm a former colleague. I think, you can look at all the Nature papers and track record and so forth, and it's really there. So yeah, I think Yale is here to stay and here to grow, as far as I can tell.
That's right.
On that question, is there, there's clearly the hardware side, and there are different players and there are different technologies and so on. There's also a software side and algorithms. So on some of that has a very different resource requirement profile. So any comments on that as to how you see this whole market evolving?
Yeah, I'm not sure if you mean at Yale or beyond. I mean, also Yale, we have a pretty strong computer, Dan Spielman and people like that are professors. They're, really excellent people. And I think there's a lot of recruitment from what I can tell now. At the same time, there is a shortage of really well-trained quantum experts at the level that the field is growing and needed. And there's a lot of, I think, interest from different communities to join and merge, because quantum computing isn't one thing, right? It isn't physics, it isn't computer science, it isn't engineering. You need all of those to make it work. So workforce development is a big issue at, I think Yale, IBM at the national level. There's a lot of funding and grants. I'm teaching a summer school in several weeks on quantum machine learning, along with other people. Last time I taught on quantum hardware development. So the software, if you want, the computer science part of it is just as important as the hardware. The hardware, if you don't have the hardware, then you can't do the computer science, of course, part of it, the quantum computer science part of it. But we increasingly need people to write compilers, transpilers, algorithms, new software languages to abstract things, to make things more modular and easy. And there's a lot of interest in that as well. So I think it's essential.
It's interesting. Yeah. Daniel, you had a little bit of a, I guess I'll just call it a late question if you want to ask, and then it looks like Phil had maybe a couple of thoughts, and then we're probably going to be wrapping up. Daniel, did you?
Yeah. Okay, sure. I'm a non-physicist, but I'm like a total physicist wannabe. I wish that I had continued in the little period at the beginning of Yale when you have several days to pick stuff. I went to a theoretical physics class, and I regret forever that I didn't continue. But so you talked about resolving things and about time scale and being able to expand and contract, and my question was about intuition, because I am compelled by the intuition that you are confirming, I guess, at least at some level, that if you can look closely enough and become a probe that is smaller than what you're probing, essentially, you can begin to discern things that are going on that previously, when your probe was too big, couldn't get into the crevices, if you know what I'm saying metaphorically, and you can begin to see stuff that you couldn't see there before. So I'm just wondering, it's a different field, particle physics, and this notion, when I read a Neil deGrasse Tyson, say thing, oh, quarks, bosons, leptons, these are fundamental particles. They are believed to be the smallest things that exist, and there will be nothing smaller than that. And my intuition tells me, just like you found detail in the discreteness of that jump, and it's not discrete, that it's completely against my intuition that these particles are fundamental. My intuition, as ridiculous as it may sound, is that it's never ending. It's going to keep going down as far as we are able to look. That's quite philosophical. I just thought if you have any, these other philosophical questions, you have been very research and lab focused. You haven't been able to comment, but I'll just go one step further and say, my intuition is also that when we can adopt the right point of view or framework, we will also discover that the speed of light is not the fastest thing that is out there. It is just something that is kind of completely endemic to our point of view of the universe. So anyway, there's some very bold statements. You're the physicist. Let me know how ridiculous those are. That's my intuition.
No, I think you're right. I think you have to constantly question things, right? Like the thing, to take this earlier experiment, the canon was that quantum jumps are like this, right? That was the canon for most people, except for QT, which is one minority group of followers, so to speak. So I agree. You have to follow intuition. Of course, you have to hear criticism and see if you can address it. Can things be faster than the speed of light? I mean, there's been such a strong downpour of, it has to be, maybe we have to also double check and examine that, right? There's nothing that says that another part of the universe, the laws of physics are indifferent, right? And, discussions about that with some very top-notch physicists, and we can look at that. So, you know, I think this reminds me of the old joke about atoms. I don't know if you know this one. Speaking of atoms and them being indivisible, you know, why can you never trust an atom? Why can't you trust atoms? Because they make up everything. Right. So, you know, that trust atoms, but that's trust and verify, right? That's the saying, I think, trust and verify. So, you know, I think we should be open to ideas like that. The other thing, as I'm sure you've read from Neil deGrasse Tyson, all these folks, is that particle physics, and you know, this is a generalization, but you know, it's kind of like smashing Swiss watches, and you know, looking at the pieces of the broken complex machines and trying to figure out how the thing works. So, you know, getting instrumentation, getting more precise measurements, speaking of which, quantum physics and tabletop quantum experiments can now start to probe some of these higher energy physics as well. Having that is going to, I think, necessarily and unavoidably open views and doors to views that we haven't had before. So I do think our view will change, and that's what's always happened.
That's great. Thank you. We're down to a couple of minutes. Phil, why don't you take us home, and then we'll.
Oh, yeah,
so it was so interesting to hear your discussion about, you know, continuous versus a discrete jump. And I'm thinking, studying mathematical logic at Yale, everything was based on the law of the excluded middle, you know, which is, you know, so I'm curious if you know, if maybe the two-valued logic idea could be re-examined, you know. The other thing I just want to ask, so around the time that I was an undergraduate at Yale, we got mini computers in the physics department, and you know, those devices were possible because transistors were able to be concentrated onto chips. And I'm wondering if qubits, you know, will ultimately be on chips, maybe at room temperature, low cost.
Great question. Thanks, Phil. Yeah, I think for the logic, you're totally right. So this Bayesian update that we mentioned earlier, you can write this, I think, in terms of logic. And I think there's a little bit of work on that, maybe not too much, but these are logical statements. What happens is I learned something about the system, you know, therefore this and this. So you can actually formulate this, I think, in some sense as logical statements, and they're a little bit more complicated than binary yes or no. Because of the quantum aspect of it. So that update is slightly more advanced, but I think underneath that, it's actually logic. And you can, and if I gave you the full talk, I can describe why it's a tangent curve based on a cat analogy with, you know, how things update with the cat runs fast when it thinks nobody's looking and stuff like that. So there's logic there. For the chips part, yes. So all the stuff that we did at Yale and we're doing at IBM now is on chips. It's on silicon chips, it's on sapphire chips. These chips get cooled to very low temperatures so that the noise is minimized, so that the environment is as quiet as possible. But they're chip-based, and they're pretty small already, the features on these chips. Like I mentioned, you know, IBM's announced the biggest to make chip in the next couple of years, 1,000-something qubits. So it's moving in that direction.
That's fantastic.
Yeah.
Yeah, that's fascinating. So we had a really enjoyable quantum physics 101 tonight. Maybe we'll do a 100-level course or 300-level course at some point. Zlatko, thank you so much. You're just so enjoyable, and there's always a sign of you know, really mastering your field and intelligence is to make it understandable by, you know, schlubs like us. So thanks so much for participating tonight. Thanks to all of you for joining. Great questions and great involvement. Come again next week. We'll have the next episode, as we said, on career pivots a couple weeks out, another STEM show, and also let us know if summertime sounds like something we'd be interested in. You can email me, email the group, Steve Bloom or Kate. Just let us know. Yeah, that makes sense. A couple nights a month, a couple every other week, or see you in the fall, or more or less. We'd really like to hear from you. You've just been a great community, great audience, and we've made some real lasting relationships here as well. So thank you, Zlatko, and thank you everybody for joining tonight, and I hope to see you next week.